Hey, what's up, guys? This is Chung here again. So let's take a look at this one, 1705, maximum number of eaten apples. Mm, so I'm gonna give it my own upvote. So you're given like a special apple tree that grows apples every day for n days, okay? And on the ice day, the tree grows apples, ice number of apples that will rot after this number of days. So which means on day I plus days I, the apples will be rotten and cannot be eaten. And on some days, the apple tree does not grow any apples, which are denoted by 00. And you can only eat at most one apple per day to keep the doctors away, okay? If there's any apple that has not uh, got rotten yet. And here note that you can keep eating after the first n days. So which means that, even after the first n days, if there's still some like apples left, you can still eat them. So given two integer arrays, days and apples, and you need to return the maximum number of apples you can eat. So for example, right, so this one on days on the first day, on day 0, the apple trees can make like one apple that can last 3 days. So which means that on day 3, this one will be rotten. So on day 2 here, we have 2 apples who will also be so this one will also get rotten in day 3 or day 4, whatever, or either 0 base or 1 base. Same thing for this one, 1 for 1, right? So this one on day 3 here, we have 3 apples that will be rotten in 1 days. So that's going to be also another 3 apples that will be rotten on day 4. Okay, so on and so forth. And so in the end, we can eat at most 7 apples in total. So yeah, and here are some constraints, right? Cool. So I mean, this one, mm, I think a normal approach is that, let's say if we have on a certain day, on the ice day here, let's say we have some apples, right? We have some apples here, apple here, we have some apples here. So I mean, a, a common or a reasonable approach to that is that we always want to eat the apples that will got rotten first. So let's say we have these 3 apples. So let's say this one, let's say we have the ice, let's say the current day is day 3. And if we have this 1 apple that will be rotten in day 4, and then we have like another, so this one will be rotten in day 6, this one will be rotten in day 5. So obviously we always want to eat the apples that will that's close to the current date, right? The rotten date is close to the current date. That's how we can eat as many apples as possible. Yeah, I think that's the basic idea for this problem. And to keep the closest date for all the apples, right? I mean, a common approach is by using a priority queue, right? Where the in the priority queue, basically for each of the elements in the priority queue, we'll save 2 numbers. So the first one is the rotten date, right? Days that the apples will get rotten. And then the second one is that the number of apples. Okay, right? And then we just get every time when we try to eat an apples, we just get the first one of the priority queue, which is the smallest date, right? And then we just decrease the apple by 1. And then after that, we check if the current element if the apple has been decreased to 0. If it is, then we should remove this one out from the priority queue. Because so why is that? Because at each new date, we're gonna insert this same we're gonna insert the element into the priority queue. So which means that at the same day we could have multiple numbers element. For example, this one, right? So here we have at the day one here, right? So we have one apple, right? That will got rotten in day three. That's why we have three and one. And then at the day two here we have what? We have another one, which is we have also got day three gonna be the rotten date, but the apples we have two. And in day three here we also have like three, and then we have three. So that's why every time when we have decrease numbers from this one, we're gonna remove this one. So as long as this number of apple becomes zero, we'll remove it so that the next time we can consume the next one in the priority queue, right? Yeah, and that's that. So we just keep doing it, and oh, and one more thing, and every time when we add a new date here, we'll also be removing the priority queue first, because let's say if we are at day three, right? If the I is three here, and we still have some uh, apples that's left in the priority queue, right? Then it means that anything that's either equal or smaller than the current date, those apples they will all be rotten, right? So which means that we will need to pop those those elements out from the priority queue. Yeah, and that's that. So that's the only two things. And then of course in the end, we also need to handle this one, handle this special case, which is you can keep eating after the first n days. Cool. So I'll try to explain a little bit more while I'm doing while I'm coding. So first thing first, we're gonna have the priority queue, right? And then we have a length of apples, and we're gonna have like an answer equal to zero, right? So for I in range of n here, okay, and if apple is not empty, right? Because we could the tree could produce nothing on the day. That's why we only gonna insert into the queue when the apple is not zero, and then which insert right to the priority queue. Like I said, so the first one is gonna be the date, right? So the dates those apples will be rotten. That's gonna be day I plus day I, right? And the apple will be the apples I here. So the reason I'm using a list instead of like a tuple is that later on I'll directly modify these apples here. If we do a like tuple like this one, I cannot do an in-place modification. That's why I use a list here. So and here remove pop out the rotten apples, right? So basically, while the priority queue is not empty and the priority queue dot zero is smaller, equal or smaller than I, then I just heap queue dot heap pop, right? So the reason I can pop from doing the priority queue pop is that the the PQ0 is always the earliest date, right? So that's why I can always do the pop from the left by using the current date. Okay, and then eat an apple, right? Who has the earliest, right? earliest rotten date, right? Here. So here we need to check the priority queue one more time. If the priority queue is not empty, because it's possible that there's no apples left at the moment. And if this one and yeah, so if the priority queue still has some apples left here, and then we just need to actually do an answer plus 1, right? Because we have eaten an answer, and then we have eaten an apple, and then we just need to decrease the priority queue 0, 1 by 1, right? That's going to be the number of the apples left. And then if the priority queue 0, 1 is empty, sorry, it's 0, we just heap queue dot heap pop the priority queue, right? So if there's nothing left of the current element, we just pop this thing out. So that's that. Okay, and let's handle handle the the case that after the n state we still have some apples left in the priority queue. So now we have n I equals to n here, right? So same thing, right? Priority queue, whenever the priority queue is not empty, I can just literally just copy this part, okay? To here. It's basically the same logic. The only difference that now we don't have any new apples coming in, but at the each day here, it's still the same logic here, right? To pop all the rotten apples for the current date, and then we eat an apple, right? And whenever the priority queue is empty, then that's when we stop. Okay. And here, don't forget to increase the I by 1. And then here we just return the answer. Yeah, I think that's it. So if I run the code here, accept it. Yeah, so that's it, right? The So the time complexity, right? So I mean the time complexity for this one is, so the priority queue is it's like it's n log n. Yeah, so I would say it's n log n, right? Because we have a of n here, and each time, and for each of the elements we have a priority queue, which is going to be the log n here for push, pop, and same thing here, right? So here is also like the n log n. I would say that, right? Because let's say we have like a big days, right? Here after this end state, but still like this here is an n, right? So it's the same as the apples. That's why the n is like the 2 to the, I mean, this is the 10 to the power of 4. So yeah, I would say the total time complexity is n log n. Yeah. And the space complexity is O of n, right? So the priority queue, uh, yeah. So the worst case scenario is we're gonna input every, so the priority queue can have like up to the number of elements of the length of the n here. Yeah, I think that's it, right? I mean, this is mm, like a typical use of the priority queue, so that we can implement this greedy approach, and by always eating the apple that has the earliest rotten the rot the date the rotten date, and then yeah, other than that, it's just a bunch of minor places that we have to pop the rotten apples, right? At each of the date here. And then also like if this current element has 0 apples left, we need to pop it out so that we can keep keep eating the other apples. Hmm. Yeah, actually, and then another, yeah, or you can like the not keep increasing, keep like sorry, just yeah, forget about that. So yeah, you have to keep pushing into the priority queue at each of the date here. And then the last thing is that uh, once you have finished producing the apples, then you have to basically use the same logic to keep eating the apples until there's nothing left in the priority queue. Yeah, and then there you go. Cool. I think that's it for this problem. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.